In this video, we are going to create a Simulink block using MATLAB code. The process we will use can create a Simulink block from MATLAB functions alone, or from both MATLAB functions and functions written in C. There are many applications which can benefit from the creation of custom blocks, such as signals processing, data analysis, and communicating with hardware. The block we will create in this video will read values from the touch sensor on a Freescale FRDM KL25Z board. This sensor, highlighted here with an orange rectangle, returns values between 0 and 1, not including 0 or 1, based on where it's currently being touched. If the sensor is not being touched, it returns a value of 0. This block will be compiled and loaded onto the hardware using the Embedded Coder Support Package for Freescale FRDM KL25Z board. If the algorithm your block will use does not require any C functions, you will simply be writing a MATLAB class, which will be called from within a Simulink block. However, if the algorithm will use C functions, you will have to evaluate those C functions from within your MATLAB code. C++ code can also be utilized as long as it is wrapped within C-compatible functions. We will see an example of how to do this later in the video. Let's take a sneak peek at the finished block. Here is the library where I placed the final block. After dragging this block to a new model, I will double-click on the block to open the block's mask. This mask has a description of the block as well as parameters which change the block's behavior. The description states that the block returns 0 when the sensor is not being touched, and a value between 0 and 1 otherwise, which mimics the hardware. The first parameter listed is a checkbox which specifies whether or not this block will remember the last position that was touched. If this is checked, the block will return the previous non-zero value when the sensor is no longer being touched. The second parameter is the sample time, which specifies how frequently the block will be updated. In this example, the sample time is set to 0.1, meaning that every tenth of a second the block will return the current value from the hardware to the Simulink model. Because this block needs to communicate with the physical sensor on this microcontroller, we will need a driver that allows us to read values from the hardware. Luckily, there is a driver for this sensor available from embed.org, an online repository and compiler. The repository that contains the driver is called TSI, which stands for Touch Sensor Interface, and it contains two files, tsisensor.cpp and tsisensor.h. These files define a C++ class for interfacing with this sensor. Because the driver code is a C++ class, but MATLAB only supports the evaluation of C functions, we need to create something called a C wrapper file, which contains C-compatible functions that use this TSI sensor class. The two files we will need to create are touchsensor_wrapper.cpp and touchsensor_wrapper.h. Once we have the C-compatible functions we need, we will create a MATLAB class called touchsensor.m, which can be used inside of a Simulink block. Before we jump into the code for this block, let's take a second to review how Simulink works. At a high level, a Simulink model contains several blocks, and when this model is simulated, Simulink initializes each block, then begins to evaluate the blocks at a certain rate and order. The time between one evaluation of a set of blocks and the next evaluation of those same blocks is called a sample time. We call it this because it defines the rate at which we are sampling the result of that set of blocks. At the end of a simulation, Simulink runs any code that a block specifies is necessary to run to clean up after itself. Here you can see an example of the TSI class being used to blink an LED. First, the header files embed.h and tsisensor.h are included. Embed.h is also from the embed.org repository, but it is already included in the support package we will be using, so we do not have to worry about getting it. In the main code, a PWM object is created, which, in this case, is driving the red LED on the hardware. Then a TSI sensor object, called TSI, is created. After that, the code goes into an infinite loop where we simply read the current position that's being touched on the sensor using the read percentage function, and subtract that from 1 and use the resulting value to set the brightness of an LED. Now that we've seen how the C++ class can be used, let's take a look at the C-compatible functions that we will be evaluating in MATLAB. First, we'll look at the header file, touchsensor_wrapper.h. We see here that the file defines 3 functions. These functions have been created to align with how Simulink works. There's a function to do initialization, one to be evaluated at every time step, and one to perform any cleanup necessary. The source code for these functions is stored in the file touchsensor_wrapper.cpp, which is similar to the C++ code we saw earlier. First, the header files embed.h and tsi-sensor.h are included. Then a variable, tsi, is created to store our tsi sensor object. In this case, we're creating a pointer in the global space so that all 3 of our functions can utilize this variable. In the first function, mw_touchsensor_init, we see that we're simply creating a new touch sensor object and storing it to the variable tsi. In the function mw_get_touchsensor_position, we are calling the read percentage function, just like in the C++ code. Then, in the mw_touchsensor_terminate function, we are deleting the tsi pointer in order to free up the memory we dynamically allocated in the init function. An important thing to notice is that all 3 of these functions are defined using the keywords extern C, which allow these functions to be linked using a C compiler, and this is why we call this file a C wrapper file. Let's take a look at the MATLAB code that will define the block. Here's the definition of the class that was used to create this block. I named the class TouchSensor, and it inherits from 2 classes, the matlab.System class and the coder.externalDependency class. The matlab.System class is what enables us to include this code in a Simulink block, and the coder.externalDependency class is what allows us to reference C code in our MATLAB class. This class has 4 sections in it, 2 property sections and 2 method sections. The property sections define variables for the class, and the method sections define its functions. The first property section has the attributes of logical and non-tunable, and it defines one property called remember position. Since this property is logical, it can only be set to true or false, and it will also show up in the block mask as a checkbox, which we saw earlier. Being non-tunable means that it cannot be changed while the model is running. The comment above the property is used in the block mask for this class. Specifically, the text listed, "Remember the last position touched," will be shown automatically in the block mask for this property. The next section defines the hidden properties. These properties will not show up either in MATLAB or in the Simulink block mask. The 2 properties that are defined here are last position and sim_sample_num. We will store the last position that was touched in the property last position, and if the remember position checkbox is checked, we will output the value stored in this property when the sensor is not being touched. The sim_sample_num property allows us to track which sample we're on when we run this block in simulation in Simulink, or when we run this code in MATLAB. The first method section defines 3 functions, the setup, step, and release implementation functions. These functions are used by the matlab.System class we are inheriting from, and they specify what this block will do during initialization, execution, and termination. The setup implementation function specifies everything that needs to happen to initialize the system. The step implementation function contains all the code that needs to be evaluated at every time step, and the release implementation function contains any code that needs to be run in order to release any resources that were allotted to this block. We see here that the setup implementation function contains one if statement. The code inside this if statement will only be run when this block is being used for code generation, either through MATLAB Coder or when building a model that contains this block. When we generate code for this class, we use the function coder.CInclude to include the header file touchsensor_wrapper.h. Once we've included the header file, we can utilize any of the functions that are specified within it. In this case, we are going to evaluate the function mw_touchsensor_init using coder.ceval. The step implementation function starts by initializing the output, touched position. Then it goes into the same if statement we just saw in the setup implementation function. When we generate code for this class, we again use the functions coder.CInclude and coder.ceval to access one of the C functions we saw earlier. In this case, we're evaluating the function mw_get_touchsensor_position, which returns the position sensed by the hardware. After retrieving the value from the sensor, we check if the Remember the Last Position Touched checkbox is checked, and if the hardware has returned the value 0. If this is the case, then we return the value stored in the property last position. And finally, we update the property last position with the last position that was touched. If we are not generating code for this class, meaning we are either simulating a model containing this block or running this code from within MATLAB, then we return the value from the sine wave specified here. This sine wave is scaled and biased in order to output values between 0 and 1, similar to what we would expect from the actual hardware. Additionally, we iterate the property simSampleNum in order to continue to maintain which sample we're on. The release implementation function looks very similar to the setup implementation function. Again, it has a single if statement in which it uses the functions coder.CInclude and coder.ceval to include the header file touchsensor_wrapper.h and then evaluate the C function mw_touchsensor_terminate, which frees memory that was dynamically allocated in the setup implementation function. The last section in this class defines 3 more functions. These functions are used by the coder.externalDependency class that we inherit from to specify what code we're dependent on. The first function, getDescriptiveName, returns a string that describes the block. This can be anything. Here we have used touchSensor. The function isSupportedContext returns a logical value, true or false, specifying whether the current context needs to know about the source files we depend on. The context, which is passed into this function, can take on many values, but we are specifying here that we only need the C++ files when we are generating code for this class. The updateBuildInfo function is used to specify what source code and header files this block is dependent on and where they're located. It starts with a similar if statement that we've seen before. Then it calls the function getTouchSensorRootPath, which returns the root directory where this block code is stored. When we evaluate this function, we see that it returns the path C documents MATLAB touchsensor, which is the location that this file is stored. It is also the root location where the source directory, include directory, and dependencies directories are located for this block. These directories contain all the source and header files we looked at earlier. Once we have this block root path, we use it to specify the locations that have header files that we depend on. The C wrapper header file is stored in the include directory, and the TSI sensor header file is stored in this subdirectory of the dependencies folder. We then specify which header file it is that we need to include. In this case, you see TSI sensor.h. We do not need to specify the file touchsensor_wrapper.h because we already included it earlier using coder.CInclude. We also use this function to specify where the source files that we depend on are located, and then we list the source files that we depend on. Here you can see TSI sensor.cpp and touchsensor_wrapper.cpp are specified, which are in this subdirectory of the dependencies folder and the src folder respectively. Now that we've seen all of the code that specifies this class, let's create an instance of this class in MATLAB. I'll be creating a variable called TSI for Touch Sensor Interface. The MATLAB code for this class lives in the folder called +FreedomBoard, which makes it part of the package called FreedomBoard. We can create an instance of this class using the syntax freedomboard.touchSensor, shown here. When we do this, we see that we have created a variable that is a MATLAB System class named freedomboard.touchSensor, and it has a single property, remember position, which is currently true. The properties that we defined earlier as hidden do not show up here. Once we've created this variable, we can use the function step, which we inherited from the matlab.System class, to evaluate the code in the step implementation function of this class. Here, I'll create a for loop from I equals 1 to 1000, and on each iteration, I'll store the result from the step function into a variable called TSPos for touch sensor position. After evaluating this for loop, we now have a variable in the workspace called TSPos, which is a 1 by 1000 array of singles. This array should contain values from our simulated behavior, meaning that it should contain a sine wave. To test this, we can simply plot the variable TSPos, and here we see that it is indeed a sine wave and that the values go between 0 and 1 as we expected. Now that we've verified this code is working in MATLAB, let's see how to use this code in Simulink. As I mentioned earlier, we will be using the Embedded Coder Support Package for Freescale FRDM KL25Z board. This support package comes with an app called the Freescale Cup Companion app, which we can use to create a new model that's already set up for this hardware. Once we have this model, we can add a MATLAB System block to it. In our 2014B, Simulink got a new feature that allows you to add a block to a model by typing its name into the model. So when I type MATLAB System, I can see that this block is stored in the user-defined functions library, and I can select it or press Enter to add it to this model. Initially, this block shows up as being unspecified because we have not yet specified which class the block should use. Here we can specify the freedom.touchSensor class just like we did in MATLAB. Once this is specified, the block takes on the characteristics of our MATLAB class. If we double-click on the block, we will see its block mask. This shows the checkbox for Remember the Last Position Touched, which we saw earlier in the code. It also provides us with a link to go directly into the source code for this block. If we want to check the simulation behavior for this block, we can add a time scope, connect it to the block, and then run it in simulation. Well, we expected to see a sine wave, but all we see is a slightly curved line. To figure out why this is happening, we can look at the sample time of the model. I'm using this button here to visually represent the sample times used in this model with color. Here we see that the sample time for this model is 0.2 seconds, and we're running this model for 10 seconds, which means that instead of running the 1,000 samples like we did in MATLAB, we are only running for 50 samples, which means that we're only evaluating a 20th of the sine wave that we viewed in MATLAB. We see in the block mask that there is currently no way to specify the sample time for this block. However, we can change the sample time of this model using the Configuration Parameters dialog by changing the value specified here as auto to some other value. Doing this, however, may not work for more complicated models because this block does not specify its own sample time, it inherits its sample time from whatever it's connected to, which means that one way to ensure that this block has a specified sample time is to connect it to something that has a sample time we can control. This can be done in many ways, but for this block I will bias the signal with a constant of 0 using the add block. This will not only allow us to control the sample time of this block, but the scalar addition of a constant 0 can be optimized out by the compiler, so this will not slow down the final block running on the hardware. Now, if we specify the sample time for the constant block to be 0.01 and update the model, we will see that the touch sensor block has inherited the sample time, and the entire model is now running with a 0.01 second sample time. Now when we simulate the model, we see the sine wave that we expect. Now we've seen all the steps required to create a new Simulink block from a MATLAB class. We've seen how the MATLAB code specifies what is going to be executed during code generation or simulation. We've seen how to evaluate C functions in MATLAB as part of code generation, and we've seen how C++ code can be used through C wrapper functions. Although we now have a functional Simulink block, there's still a couple of things that we can do to package the Simulink block and make it look more like the block we saw in the beginning of this video. The following steps will show you how to create a nice block mask, add sample time to the block mask, and redistribute this block to others. First, we'll open up the model that we previously created. We saw earlier that the touch sensor block, the add block, and the constant block can work together to allow us to specify a sample time for the touch sensor block. We can select all three of these blocks and create a subsystem, which I will rename touch sensor. Then we'll create a mask for the subsystem by right-clicking on the block and selecting the Create Mask option under the Mask menu item. We can add parameters to this mask from the blocks contained within the subsystem using the Promote parameter. We'll first promote the Remember the Last Position property of the class that we created earlier. Then we can promote the Sample Time property of the constant block. If we preview the mask, we now see that both parameters that we want are there. You can now add an image to the block using the same method you would for any normal subsystem. In this case, I have an image in the Resources directory that I will load. I will also specify some text to be added to the mask. After applying these changes, we see that the block mask now has the image we specified, and when we double-click on the block, we see the parameters we expect on the block mask. Now we can create a simple model to test the code generation capabilities of this block. This model will use the touch sensor to control the brightness of the red LED on the board, just like the example C++ code we saw earlier. First, we will add an RGB LED block to the model. Then we will connect the red LED to the signal coming out of the touch sensor. The RGB LED block expects values between 0 and 255 in order to power the LED. We have to add a gain block here in order to scale the values from the touch sensor, which is between 0 and 1, to a value that will control the LED appropriately. Then we can add a constant block to the model in order to make sure that the green and blue LEDs are always off. Finally, we can build the model, which will generate code for this model, compile it into an executable, and then load it onto the hardware. Let's see what it does on the board. Here we can see that the brightness of the LED changes depending on where I touch the sensor. We also see that as I lift my finger from the touch sensor, the LED's brightness remains constant. With this model, we can also quickly see what happens when we uncheck the Remember the Last Position checkbox. This time, we see that even though the brightness of the LED changes depending on where I touch the sensor, when I lift my finger from the sensor, the LED turns off because the sensor is now outputting 0 to the LED instead of remembering the last position that was touched. Now that this block is working for us, we can add it to an empty library that we can distribute to other people, as long as we have also sent them the touch sensor directory, which contains all the source files and resources that this block requires. You've now seen how to create a Simulink block using MATLAB code. The files shown in this video are available for download on the File Exchange at the link provided here.